minus dr by r is equal to k dt, or else you can take this negative sign here as well. So what you are going to do now, in the next step you are going to integrate these two. ln r0 will be equal to minus k into 0 plus I. So from that what you will get, what is the value of I? I will be equal to ln r0. If we plot ln r against t, we get a straight line with slope minus k and intercept is equal to ln r. For the time t1, ln r1 will be equal to minus k t1 plus ln r0. R0 will not change, right? It is the initial concentration. Hello everyone, this is Ambli Unnikrishnan from the Department of Chemistry. So today I am back with session 3 of the chapter Chemical Kinetics. So in the last session we studied order and molecularity of the reaction, right? So today we are going to study an important part, that is integrated rate equation for a zero order and first order reaction in detail, and then what is the significance of first order rate equation as well as the rate constant for first order gas phase reaction. So let us begin with the first one, that is integrated rate equation for a zero order reaction, right? So what is a zero order reaction? Is the one in which the rate of the reaction is independent of the molar concentration of the reactant, right? So we already know that. So we are taking a general expression here, that is reactants giving products. R is a reactant, P is the product. So how do you write the differential rate equation for this? In the first session itself we have studied, that is d by dt minus d by dt, this minus is important, right? Minus d by dt of molar concentration of R is equal to K into R to the power 0. So what is this? From where did it come? Rate is equal to K into A to the power 0. We know this. So this is the rate expression or rate law, and this is a zero order reaction. You can say it is A to the power 0. So instead of writing this rate here, we have taken this equation, that is minus dr by dt. Minus d by dt of r is equal to k into a to the power 0, right? We already know that rate is equal to minus d by dt of r, right? So that is the equation shown here. Now as any quantity raised to the power 0 is unity, what happens? This term will become 1, right? So what you will have, rate is equal to minus dr by dt is equal to k into 1 you will get. This r to the power 0 will not be there, it was 1. So what you will have? Now from this what we are going to do? We will get minus dr by dt is equal to k. This is what we have, k into 1 is k itself. Now we are going to take this dt to the other side. So you will have minus dr is equal to k dt. Right, you will get like this, or else you can take the minus to the other side. This minus we can take it other side, so you will get dr is equal to minus k dt. I hope till here it is clear. So now what we are going to do is we are going to integrate on both sides. We are going to integrate on both sides. So what is integral of dr? It is r itself. Right. Now what is integral of minus k dt? K is a constant, so you can take it outside, and the minus sign also you can take outside. So you will have minus k here. Now what is left here? Minus integral dt. What is integral dt? It is t itself. So you will have minus kt and plus I will be there. That is the constant here while doing integration. So integral dr will give you r. Minus k is a constant, took it outside, integral dt is t. So this is what you are going to get. Now where I is the constant of integration, right? Now at time t is equal to 0, the concentration of the reactant will be R0, right? So now if the time is equal to 0, that means initially what we are going to consider here is the molar concentration of R, we are going to write it as R0. That means it is the initial concentration, right? So where R0 is the initial concentration of the reactant. Now substituting in equation, that is substituting in the first equation, what we are going to do here is we are going to take the time as 0. Right, we are going to take the time as 0, then what happens to R? R will become R0. So what you are going to get? R0 will be equal to minus k into, in place of t it will be 0, right? Plus I. So what you will get? R0 is equal to I. K into 0 is what? 0 itself. What you will have? I itself. Right. Now substituting the value of I in the equation 1. Now you got the value of I here. Now what we are going to do is that I, that is R0, we are going to substitute here. So what you will get? R is equal to minus kt plus R0 you will get, right? So R is equal to minus kt plus R0. This I value we are substituting here. Right. Now further simplifying equation 2, we get the rate constant. That is, we are just going to rearrange this. We need it in terms of rate constant K. So you have the equation as R is equal to minus kt plus R0, right? This is the equation you are having. So I need it in terms of K. I am going to keep the K as it is. What I am going to do, I am going to bring this here. So you will have R0 minus R divided by T. This is what you are going to have, right? So you can bring the KT to this side, so it will become plus KT. You can take the R to the other side, so it will become minus R. So K will be R0 minus R by T. So this is called as the integrated rate equation for a zero order reaction, that is K is equal to R0 minus R by T. So you can expect numericals from this part as well as the derivation of this integrated rate equation for a zero order reaction is important, right? Now comparing equation 2 with the equation of a straight line y is equal to mx plus c, if we plot R against T, we get a straight line with the slope minus K and intercept equal to R naught. So this equation, if you are comparing it with y is equal to mx plus c, we are comparing it with y is equal to mx plus c. So what is y? Concentration. So y is concentration of R. What is mx? You have x, right? X is your time. Time is here, and what is m in the equation? Y is equal to mx plus c. What is m? M is slope, right? So what is the slope you are having? Minus slope you are having, right? K is equal to minus of slope. So what you are getting, if you calculate the slope, which will give you minus of the rate constant, right? So from this equation you can also calculate the rate constant through the graph, right? As well as what is the y-intercept you are having, that will be the initial concentration of the reactant. So y-intercept is the point where it touches the y-axis, right? So this is the initial molar concentration of the reactant, right? And the negative of the slope will give you the rate constant. Now moving on to the integrated rate equation for a first order reaction. So here also you have the general equation, reactants giving products. So in a first order reaction, what will be the equation? Rate is equal to K into A to the power 1, right? A to the power 1 is A itself, right? So now instead of writing R here, what we can write? Minus dr by dt. Again we can write it in the same format, which is equal to K into A. That is what is written here. Minus dr by dt is equal to K into R. So instead of A, you can write R as well, because we have taken this particular equation here. Now what we can write? Or else dr by dt is equal to K dt. So from this we can just equate these two, that is minus dr by dt is equal to K into R. Now integrating on both sides. Again we are going to integrate here as well as here. Okay, so now we are going to see the integrated rate equation for a zero order reaction. Again we are going to consider a general equation, that is reactants giving products. So here also rate is equal to minus dr by dt, which is equal to K into R. So this is a first order reaction, so rate is equal to K into molar concentration of R, right? So instead of rate, you can write D minus dr by dt, which is equal to K into molar concentration of R, right? So now what we are going to do, let's take the reactant terms together. So what you will get? Minus dr by R. Minus dr by R. I am taking this R to the denominator. So what you will have? This dt I am going to take here. So you will get K dt. So minus dr by R is equal to K dt, or else you can take this negative sign here as well. So what you are going to do now, in the next step you are going to integrate these two. Now what is integral of dr by R? It is ln R, right? It is ln R, and here also integral you are taking, K will come outside, right? And you have dt, integral of dt is what? T, right? So you have ln R is equal to minus kt plus I. So here you can see this negative sign is being taken here, that's it. So ln R is equal to minus kt plus I. This I is the constant of integration. Now again in the same way how we have done for zero order reaction, at time is equal to 0, what will happen? Initial concentration R will be taken as R0, right? At time is equal to 0, R will be R0, where R0 is the initial concentration. So now what we are going to do? We are going to substitute in this equation. So what will happen? This T will be 0 and ln R will become ln R0, right? So ln R0 will be equal to minus K into 0 plus I. So from that what you will get? What is the value of I? I will be equal to ln R0. Now that is, again we are going to substitute in the first equation. So in place of I, what you will substitute? You will substitute ln R0. So ln R is equal to minus KT plus ln R0. So again you are just going to rearrange. You take the KT to this side, ln R to this side. So you will get KT is equal to ln R0 minus ln R, right? KT is equal to ln R0 minus ln R. So you will get like this. Now what you are going to do? K is equal to, now ln R0 minus ln R. What is that? ln A minus ln B. What is ln A minus ln B? It is ln A by B, right? So you can write KT itself. KT is equal to ln of R0 by R, you can write. ln, this is in the format ln A minus ln B. So you can write it as ln A by B. Right. Now you can take t to the other side. So you will get k is equal to 1 by t into ln R0 by R. Right. So this is the other equation you can have. So this is in the form of ln. Now you can convert it into log by multiplying it with 2.303. So what you will get 2.303 by t log R0 by R. This is in the format of ln. If you multiply this equation by 2.303, you will get this equation in terms of log. So this is the integrated rate equation for a first order reaction. K is equal to 2.303 by t log R0 by R. So these two derivations are important. That is for a zero order reaction and a first order reaction, the integrated rate equation. Right. Now moving on to the significance of first order rate equation. That is from the first order rate equation or the integrated rate equation, what are the factors or what are the concepts that we can understand? The first one is consider ln R is equal to minus kt plus ln R0. So that is this particular equation. Ln R is equal to minus kt plus ln R0, but after substitution. So comparing this equation with y is equal to mx plus c, if we plot ln R against t, we get a straight line with slope minus k and intercept is equal to ln R. This equation we are comparing it with y is equal to mx plus c. So in that case, y is what? ln R. M is what? You have the minus k. So slope is minus k. X is what? T. And y-intercept c is ln R0. So if you plot a graph, what you will get? ln R versus time. If you are plotting a graph, you will get a slope like this, and the k will be minus of slope, or else you can also write it as, once you calculate the slope, you will get minus of the rate constant, right? And the y-intercept will give you ln R0. Now the first order rate equation that we have studied is k is equal to 2.303 by t log R0 by R. Now log R0 by R is equal to, that is this term we are keeping as it is, this part we are going to take it to other side. So what will happen? This will go to the numerator and 2.303 will come to the denominator. Just rearranging it. So you will get log R0 by R is equal to kt by 2.303. So now if we plot a graph between this log R0 by R versus t, the slope will be k is equal to 2.303. That is, again we are going to consider this equation or compare this equation with y is equal to mx plus c. So in that case, y will be log R0 by R. Now if we are comparing this equation with the equation of a straight line, y will be log R0 by R, right? And x will be what? X will be t. Now whatever is left, that is k by 2.303 will be m, that will be the slope. So if you are plotting a graph between log R0 by R and time, you will get a graph like this, whereas slope will be equal to k by 2.303. I hope that is clear. So if you are taking ln R versus time, what is the slope, and what is log R0 R versus time, if you are taking, what is the slope, you have to remember. Okay. Now moving on to the next one. At time t1 from the equation, that is this particular equation, ln R is equal to minus kt plus ln R0, we are going to consider it at two different times. Now for the time t1, ln R1 will be equal to minus kt1 plus ln R0. R0 will not change, right? It is the initial concentration. And at time t2, what you will get? ln R2 will be equal to minus kt2 plus ln R0. Now R1 and R2 are the molar concentration of the reactants at time t1 and t2. Now subtracting equation 2 from equation 1. So 2 minus 1 we are going to do. So what you will have? ln R1 minus ln R2 is equal to minus kt1 minus of kt2, right? You have minus kt2 and minus kt1. So it will be minus kt1 minus of minus kt2. So that will give you plus kt2, right? So again this is in the format of what? ln A minus ln B, that is ln A by B. So you will get ln R1 by R2. ln R1 by R2 is equal to, what is this part? You will get it as minus kt1 you will have, and this minus plus minus you will get plus kt2. So what it is? kt2 minus kt1. So in this, what is common? K is common. So you can write it as k into t2 minus t1, right? So that is what is written here, k into t2 minus t1. Now we have to write it in forms of k. So t2 minus t1 we can take it to the other side. So it will come as a denominator. So you will have 1 by t2 minus t1 is equal to ln R1 by R2. So again this is in format of ln. If you have to convert it into log, you can multiply it by 2.303. So what you will get? K is equal to 2.303 by T2 minus T1 log of R1 by R2. So this is also an important equation. This equation you can use when the concentration of the reactants at two different times is given, R1 and R2 and T2 and T1. If you know, to calculate the rate constant, you can use this particular equation. So I hope that is clear. So in the next session, we are going to discuss the half-life of a reaction. So like we have studied the integrated rate equation, half-life of a reaction is also very important. So I hope the concepts that I have covered in this session is clear for you. So that's all for today. Thank you.